Hello, and welcome to this tutorial on performing time series analysis using convolutional networks. So one application of machine learning is the classification of time series data, and this is data that is in an order, usually ordered by time. So we're looking at the possibility of constructing a model of the data in order to classify unseen test instances. For that, we're going to use TensorFlow to construct some convolutional neural networks, and they will perform classification on the data. The data itself is cyclostationary, and this means that the data is separated into the distinct cycles. So we're looking at deep learning and convolutional neural networks. Convolutional neural networks have been shown to have excellent performance on image classification, and since their inception they've been applied to other application domains as well. And recent research in the area has shown that they actually have excellent classification performance on time series data. So in order to examine their performance, we're going to need some data sets, and for this we're going to use the UCR data sets. And these datasets have been used a lot in time series analysis in order to compare performance between different algorithms. And the datasets themselves contain two or more classes and are divided into train datasets and test datasets. Obviously, you use the train datasets to construct a model with your algorithm, and then you examine its performance on the test datasets. And each example of the time series data is an example of the data that is cyclostationary. A bit of history of these datasets. They were originally gathered by Dr. Eamon Koff of the University of California at Riverside, and currently looks like they're being maintained by researchers at the University of East Anglia in the UK. And if you have a look at some of the links provided below, you can see the algorithms that have been developed by these researchers and others. And a good paper to start with is one by Antonia Bagnall and colleagues, which is a review and experimental evaluation of the recent advances in time classification, which gives you an overview of the algorithms and their performance. So we're looking at convolutional neural networks, and a couple of papers recently have used these to perform classification on the UCR dataset, and they provide details of their performance. They're a little more complex than the algorithms we present here, but these will give you an idea. And below are the links where you can find more information on the datasets. Okay, so we're going to begin by constructing the convolutional neural networks and the framework in order to construct models and evaluate performance. We'll be using Python and also TensorFlow to construct convolutional neural networks. So we perform the necessary imports, also importing some other utilities that are useful, such as Keras and sklearn. Next, we need to import the time series data and pre-process it. The data can be downloaded using the sources above, and it's also scaled to the range of the ReLU activation function that we're going to use. There are actually many data sets that can be used, and we're going to use the Italy power demand dataset, as we can see that actually the convolutional neural network has excellent performance on this. And this is a dataset from 12 months of the electrical power demand time series from Italy. So first of all, we create a function to import the required UCR datasets. The dataset is in the format that each row is a sample, but the first item in the row is actually the label, and the rest is the time series data. So we import the dataset, extract the first column, which is the label, and then the rest, which is the data. Okay, so we're importing the time series locally, and then we perform some scaling on the datasets. This is to ensure that it's actually in the range of the ReLU activation function. And finally, we perform some statistics on the data that are required. For example, we extract the time series length, the number of training and testing samples, and also the number of classes. Next, the labels are extracted, and for them to be used by TensorFlow, they need to be one-hot encoded. That means that they're put into a matrix, which is m by n, where m is the number of samples and n is the number of classes. Just to show you what the time series look at, we've created a function that will plot the time series data. And below you can see some instances of the time series data with the labels. For example, class 1 has this pattern, class 0, sorry, has this pattern, and class 1 this. There are several parameters that are required for the neural network. For example, the batch size. This is the number of data instances that are fed through the neural network before the weights are updated. So the training set is actually split into batches, and these are fed through one at a time with the weights updated each time one batch has been fed through. The number of epochs is the number of times the whole training data set is fed through the neural network. And because this is a univariate time series, there is only one channel for one sensor reading. And finally, we need to specify the filters. And the size of the filters and the number of filters is set for each convolutional layer. And the filters perform the convolution operation on the data. Okay, next we're going to set up the deep learning network. And this will consist of several layers, including convolutional layers and standard layers. Okay, so we construct a function to construct the convolutional layer. And this will specify the weights, the biases, and whether pooling is used. And next, we define a function to construct the fully connected layer. So this will have weights, biases, and also the activation function that is used. And finally, there's a function to flatten the output of the convolutional layer. And this is called the flatten layer. And finally, there's a function to initialize the weights. The weights in the deep learning network will be randomly set to begin with before we alter them in order to optimize the performance on the training set. So we're ready to construct the convolutional neural network. Initially, we use placeholder tensors in order to represent the data set. So the placeholders are defined, and also the placeholders for the output of the convolutional of the deep learning convolutional neural network for the labels. So for our neural network that we've designed, it's fairly simple. We're going to have two convolutional layers, and these are stacked so that the output of one is fed into the other. And the layers also use pooling, so that the sample, in this case the time series, will be downsampled. So we have layer 1, and the input of layer 1 is the training data, and the output is fed into layer 2, so the input of layer 2 is the output of layer 1. And layer 2 also uses pooling. So once the data has passed through two convolutional layers, it enters the final layers. And initially, the output has to be flattened because it's three-dimensional. So we have a flattening layer, and then this is passed through a fully connected layer. And finally, we have a softmax layer. So softmax layer takes the output of the previous layer and squashes it so that it sums to 1 across all classes. And then the class with the highest value can be taken to be the label the network is assigning to the time series sample. Okay, so we have the specification of the softmax layer. And finally, from this, we get the predicted class from the softmax layer. Okay, so in order for the network to learn, we need to define the cost function. And the aim is to optimize the weights so that the network can predict the classes of the training data with maximum accuracy. So we have the training data, we also have the labels, so the network can know whether it's accurately predicted. And the theory is that if this is done and the network is able to generalize well, that means it's able to classify unseen test data, then it will accurately classify the unseen test data. Cross entropy is used to determine the current error, and then back propagation is used to nudge the weights in a direction that will increase the classification accuracy. So here we specify the cost entropy to be used with the cost function. And once this is complete, finally we construct the TensorFlow graph. So the elements of the graph are put together and they are initialized, and the weights are initialized that need to be optimized. So then, as we said previously, we're going to use batches because research has shown that higher accuracy can be achieved by passing the data through the network in batches and then updating the weights after each batch. And this is as opposed to passing the data set through the network in its entirety and then updating the weights. So the following function below splits the data set into batches, and often it's preferable to shuffle the data set after each epoch rather than putting the data set through in the same order each time. So in this function, we shuffle the data set if required, and then we split it into batches, which is in the form of a list, one for the data and one for the correct labels. And finally, we can evaluate the graph. So in each epoch, all the data is fed through in batches, as described previously. And if we run this function, we can see that the accuracy increases. Yeah, just to explain this a little bit, so for each epoch, we have a batch size of 20, which means 20 data instances are passed through before the backpropagation updates the weights. And as I said, at the first epoch, we've got a classification accuracy of 49.25%. This is reasonable because there are two classes, so you could say it's as accurate as randomly assigning the label. But you can see after 100 epochs, the accuracy has already increased to 88%. And then after 200 epochs, it's reached 95%. And then it's fairly consistent only with minor improvements as more epochs are performed, till finally we have a final training accuracy on the dataset of 97.01%. So we've trained the convolutional neural network. So now we have to analyze the performance on the test data. So the idea is to put unseen data into the model and see how accurate it is in classifying them. Obviously, we have the final label it should be, but we're not going to disclose that to the convolutional neural network, and it has to determine what it thinks is the correct label. We then compare them to determine its accuracy. And you can see we're feeding in roughly 1,000 test data instances, and we get an accuracy of 96.31%. So the accuracy is only slightly less than the accuracy on the training data, which is good. That shows that the convolutional neural network is actually generalizing quite well. And if we examine the accuracy on each class, so class 0, it's classified 499 time series samples correctly out of 513, and on class 0, on class 1, it's correctly classified 492 instances out of 516. So there's no kind of class mismatch either. It seems to be able to classify each class adequately. Okay, so that was the tutorial on convolutional neural networks for time series analysis. I hope you found it useful, and yeah, please have a look at the links provided in order to see some further information on the topic.